Extreme values. We'll start with a review question. So here, given the graphs of f and g below, identify any absolute extrema and any local extrema. So we'll say this is the graph of f of x. We want to find the absolute maximum and absolute minimum. Now, over the entire domain, we're looking for, is there a biggest y value? So there is a biggest y value that is a real number. It occurs right up here at the y value of 3. So absolute maximums and minimums are y values, so the answer is just 3. We can add some additional detail and say where it occurs by writing 3, which is equal to f of 2. For absolute minimum, is there a smallest y value over the entire domain? Well, since the graph goes down towards negative infinity here, and negative infinity is not a real number, I would say there is no absolute minimum. So absolute minimum, there is none. For local maximum, or maximums potentially, we are looking for, is there any interval where there is a biggest y value? So we can see that in an interval around 2, the function would have a biggest y value. So that y value would be 3. So 3 is also a local maximum. So 3, which again is occurring at 2, so 3 equals f of 2. And local minimums, is there an interval where there is a least y value or smallest y value? So the answer there is no. There is no interval where there is a smallest y value over that interval. So for local minimums, we have none. For the second function, which we're calling g of x, we're trying to find the absolute maximum. So across the entire domain, is there a y value that is bigger than all the rest? A lot of people's eyes go right here to this location. So they want to go ahead and say that the absolute maximum is 6, but actually it's not. So there are y values that come out of this function that are bigger than 6. So these arrows indicate that my graph goes up forever and ever and ever. So there are bigger y values that come out of this function over the whole entire domain. So we would write that the absolute maximum is none because positive infinity is not a real number. For absolute minimum, however, we do have a smallest y value over the whole domain. So that happens down here at this y value of negative 3. So the absolute minimum is the y value negative 3, which occurs at g of negative 1. Now, for local maximum, is there a little interval where there is a biggest y value? So the answer there is yes. Around 2, we do have a biggest y value that occurs at 6. So although this was not an absolute maximum, it is a local maximum. So 6, which is g of 2. And for local minimum, or minimums, there are actually 2. So around the interval, an interval around negative 1, I would have a smallest y value of negative 3. So negative 3 is a local minimum, which occurs at g of negative 1, as we said. But there's another local minimum that occurs. So over here, I do have a local minimum because around 4, if I create a little interval, there is a lowest y value. So this point down here that exists at 1 is the lowest y value if I think about all the y values in this interval. So I would say that positive 1 is a local minimum, and that occurs at g of 4. Let's go ahead and formalize some of the ideas from the previous example. So we have what are called extreme values or extrema of f of x. Those are the absolute maximum and minimum values of a function. And the singular version is called extremum. So absolute, or global sometimes, extrema, occur when I have a function defined on a domain D, and we would say that f of a y value, is the absolute minimum of f of x if f of a is less than or equal to f of x for all the x values in the domain. So if it's less than all of them, then it must be the minimum. So this is the formal definition. The way we think about it is the absolute minimum is the smallest y value over the entire domain. And remember, we can't use negative infinity. And then on the other hand, we have an absolute maximum of f of x if f of a is greater than or equal to f of x for all the x values in the domain. So the absolute maximum is the biggest y value across the entire domain, and we cannot use positive infinity. Now let's formalize the idea of local extrema, sometimes called relative extrema. So if we have a function f of x, we say f of c, again a y value, is a local minimum if f of c is less than or equal to f of x on some open interval containing c. So it has to be the least value over an entire interval around c. So we're looking for the y values at what I'm going to call the valleys in the graph. That's when I have a local minimum. So they can also occur at sort of those weird places that we saw before where I had a hole in the graph and then I had this point below, or just any typical valley. That's when I would have a local minimum down here at this point. And the local maximum occurs if f of c is greater than or equal to f of x on some interval, open interval containing c. So we'd be looking for the y valleys at what I call the peaks in the graph. So that would occur at something like this, or something like this, or I can even have something weird occur, like a hole in the graph, but the point be up here. So this is the highest point in some interval. So it's important to note local extrema cannot happen at an endpoint, but absolute extrema can occur at endpoints if I have a closed interval or a half-closed interval. So for notation, extrema are, remember, they are y values. So they should be expressed as f of c equals b, unless specifically you're asked for the y value at which an extrema occurs. So the answer is the y value. It tells us more if we write f of c equals b, because then we know where that y value occurs, but the bottom line is the answer is a y value for both absolute and local extrema. So the next question is, do all functions have extreme values? That was absolute maximums or minimums. No. So here we can see that just this linear function here, this x cubed function, and then this parabola with a hole right at the top of the parabola where the vertex would be, none of these have an absolute maximum or an absolute minimum. So the answer is no. All functions do not have extreme values. So the last side brings us to the extreme value theorem. When do we have extreme values? When will we have an absolute max and absolute min? Two conditions have to be true. If f of x is continuous, so I need a continuous function on a closed interval. I need a continuous function on a closed interval a to b. Then I will for sure have both an absolute maximum and an absolute minimum on that interval. Let's take a look at an example. Find the extreme values from the graphs of f of x shown. So both of these graphs are continuous and defined on closed intervals. So they have these closed endpoints. So they're going to have both an absolute max and an absolute min. So the absolute max on this first graph, we're going to call this f of x. So the absolute max occurs at the endpoint over here at the x value 9, but the y value is 3. So the biggest y value is 3, which occurs at f of 9. And the absolute minimum happens to be at the other endpoint. So the absolute minimum is 0, which happens at x equals 0. So we have 0 equals f of 0. Now the second graph, we'll also call this a different f of x. So the absolute maximum on this function doesn't occur at an endpoint. It occurs up here at a local maximum. So the highest y value here occurs at the x value 2, but it's the y value 4. So the absolute maximum is 4 which occurs at f of 2, but the absolute minimum occurs at an endpoint. So it occurs over here at the x value -2, but it is the y value down here at -8. So the least y value, the smallest y value that comes out is -8 at -2. Now we're going to define critical value. A number c in the domain of f is called a critical value or critical number if either f prime of c equals 0 or f prime of c does not exist. So we have this x value c as long as it's in the domain, and if that c value makes the derivative 0 or the derivative not exist, it's called a critical value. So how do we find the critical values or critical numbers? We set the derivative f prime of x equal to 0 and we solve for x. We find those x values where the derivative is undefined by setting the denominator equal to 0. But again, be sure that the x values are in the domain of the original function f. Here we're going to find the critical values for each of the following. F of x equals 3x squared minus 6x plus 4. So we want to figure out where is f prime of x either equal to 0 or potentially undefined. So f prime of x is 6x minus 6, and we can set that equal to 0. It can't be undefined, it's a line. So we'll just add the 6 and divide by 6, so we get a critical value of 1. We do want to make sure that 1 is in the domain of the original function, but we have a polynomial here, so the domain is all real numbers. For the second example, I have g of x is equal to x to the 2/3. So again, I want to figure out where either g prime of x is 0 or undefined. So g prime of x is 2/3 x to the -1/3. So again, where is that potentially 0 or undefined? Now we'll rewrite it as 2 over 3x to the 1/3. So it turns out that this cannot equal 0 because then the numerator would have to equal 0, but this can potentially be undefined. So I'm undefined when the denominator is equal to 0. So I'm going to go ahead and set 3x to the 1/3 equal to 0, which if I divide by 3, I get x to the 1/3 equals 0, and that only happens when x equals 0. And now we just have to make sure that this number is in the domain of the original function. And it is. I can take 0 to the 2/3. So my critical value is just 0. And now we'll find the critical values of h of x here. So we're going to want where is h prime of x equal to 0 or undefined. So h prime of x, the derivative, is going to require the quotient rule. So we have low x minus 3 times the derivative of the top, 2x, minus the top x squared times the derivative of the bottom 1 all over x minus 3 squared. So if we clean that up a little bit, we have 2x squared minus 6x minus x squared all over x minus 3 squared. Or, even more simplified, x squared minus 6x over x minus 3 squared. So I'm interested in where this is equal to 0 or undefined. So my function would be equal to 0, my rational function, if the numerator was equal to 0. So here I'm going to go ahead and split it up. So x squared minus 6x equals 0. I can factor out an x. So I have x equals 0 and x minus 6 equals 0. So I get x equals 6. And then to find where this is undefined, I would set the denominator equal to 0 or the factor in the denominator. So x minus 3 is equal to 0. So I have x equals 3. So right now I have 3 potential critical values, 0, 6, and 3. But we have to be careful because we have to make sure these are in the domain of the original function. Now on a rational function, the only value that creates a problem are any that make the denominator equal 0. So the domain is everything except 3. So we have to go ahead and remove 3 as a critical value. The only critical values are 0 and 6. So my critical values here are 0 and 6. Fermat's theorem on local extrema. This theorem says that if f of c is a local min or max, then c is a critical value of f of x. So this theorem tells us that if I have a function, so here we have a function f of x, and I identify a local min or local max. So here I have a local max, then what must be true is that that value, that x value where it occurs, -1, must be a critical value of f of x, which means -1 must be a place where the derivative is equal to 0 or undefined. Well, here the derivative is equal to 0, so f prime of -1 is equal to 0. So yes, -1 is a critical value. And then over here we have ourselves a local minimum. So we would need at the x value 1 to have a place where the derivative is either equal to 0 or does not exist. Well, right here we have that f prime of 1 does not exist because I have this sharp turn that's happening. So it is true that 1 and -1 are critical values. Before we move on, I have an important note. The converse of Fermat's theorem isn't true. So in other words, if c is a critical value, f of x does not necessarily have a local min or max. So just because I have a critical value doesn't mean I have a local min or max on the graph. So here is a counterexample to the fact that the converse isn't true. So on this graph of f of x, right here at 0, I know that f prime of 0 equals 0. So what that means is that 0 is a critical value. But notice there is no local min or max occurring there. So if there is a local min or max, then there is a critical value at that x value. But if I have a critical value, it doesn't necessarily mean I'm going to have a local min or max at that value. So now this brings us to extreme values on a closed interval. So if we know that f of x is continuous on a closed interval, well then we know that f has to have an absolute min or max. Well, we're going to let f of c be the minimum or maximum value on a to b. Then c is either a critical value or one of the endpoints, a or b. So we know for sure we have to have an absolute min and an absolute max, and that's going to occur at these values c, which are either critical values or endpoints. So we looked at these two examples before, and we said that we have an absolute min here and an absolute max over here. So notice, where did they occur? Those occurred at endpoints. Well, on the second example, the absolute maximum occurred up here, where notice I have a critical value. The derivative is equal to 0 there. And my absolute minimum occurred at the endpoint. So we have to check all critical values and both endpoints of a closed interval to determine what the absolute min and the absolute maximum value are. We're going to go ahead and find the absolute max and min of f of x equals this cubic polynomial on the interval 0 to 6. We're going to ignore the graph that's here and use it to verify our answer at the end. Typically, the graph would not be given on this type of problem. We start with finding the derivative so that we can find the critical values. So f prime of x is equal to 6x squared minus 30x plus 24. I'm going to go ahead and factor out the 6. So I have x squared minus 5x plus 4. And I'm setting this equal to 0. So factor completely, x minus 4, x minus 1 is equal to 0. And I end up with x equals 4 and x equals 1. So these are in the domain of my polynomial, all real numbers. and 1 and 4 are in the interval in question. So these are my two critical values. We take the critical values 1 and 4, as well as the endpoints 0 and 6, and substitute them into the original function to find the corresponding y values. So we find f of 0, f of 1, f of 4, and f of 6. So this is an endpoint, a critical value, an endpoint. And we go ahead and substitute in 0, well, all the x's would be 0, so all that's left is the y-intercept 7. When I substitute in 1, I get 18. When I substitute in 4 into each x, I get negative 9. And when I substitute in 6, I get positive 43. So I just made quick work of this here. We are now looking at the outputs, the y values, for the biggest number and the smallest number. So the biggest number here is 43. The smallest number is negative 9. So we'll label the absolute minimum and the absolute maximum. Now we'll go ahead and acknowledge the graph is here. So this is the function f of x defined from 0 to 6. We can see that there are critical values at 1, the derivative is 0, and at 4, the derivative is 0. But our absolute maximum occurred at an endpoint, and our absolute minimum occurred at a critical value. Now let's find the maximum of f of x equals 1 minus the quantity x minus 1 to the 2/3 on the closed interval from negative 1. Again, we will ignore the graph. So we find the derivative f prime of x is equal to negative 2/3 x minus 1 to the negative 1/3 times the derivative of the inside, which is 1. And now we need to set this equal to 0. Well, before I do that, I'm going to do a little bit of simplifying. So I'm going to rewrite the derivative as negative 2 over 3 times the cube root of x minus 1. And I want to know, where is this equal to 0, and then where is this potentially undefined? Well, this cannot equal 0 because the numerator is just a constant, but this is undefined when the denominator equals 0, and that is at x equals 1. So to be a critical value, I want to make sure I can substitute this into the function that's in the domain, and it is. If I substitute in 1, I get this piece as 0, and 1 minus 0 is 1, so that's fine. And 1 is also in the given interval. So this is my critical value, and we proceed to plug in the endpoints and critical values into f. So we have f of negative 1, f of 1, and f of 2. So again, we have endpoint, critical value, endpoint. So when I substitute in f of negative 1, I get 1 minus negative 1 minus 1 to the 2/3. And that's 1 minus negative 2 to the 2/3. Or I'll write it as 1 minus, I'm going to write this as 4 to the 1/3. So I'm taking negative 2 and squaring it, but I still have this 1/3. Now, I'd have to substitute this into my calculator to get an approximate value, but I should have number sense as to the fact that this overall quantity would be a negative value. So we know this is a negative value because 1 minus a number bigger than 1, but I can approximate it with a calculator and obtain the value negative 0.587. Now we substitute in 1. So f of 1, that was 1 minus, this would become 0, so we end up with just 1. And f of 2 is 1 minus 2 minus 1 to the 2/3, and that is 1 minus 1, so we end up with just 0. So this time we were just asked for the maximum value, so I have a negative number, 1, and 0, so the absolute maximum is 1. Now we'll acknowledge the graph. Here we have our f of x defined between -1 and 2. We can see our critical value where the derivative does not exist at x equals 1, and our absolute maximum occurring at that location as opposed to at the endpoints. Here we find the x values of the absolute max and min, given f of x is 2x squared minus 8 natural log x on the interval from 1 to 4. So we'll ignore the graph. We'll start by taking the derivative. F prime of x is equal to 4x minus 8 over x. And to set this equal to 0, or find where it's undefined, we need to combine these two terms and get one rational expression. So I have 4x squared minus 8 all over x. We're going to set equal to 0 and figure out where it's potentially undefined. So this is 0 where the numerator equals 0, so 4x squared minus 8 equals 0. That's x squared equals 2, or x equals plus or minus the square root of 2. Now I can check plus or minus the square root of 2 in the original function whether they're in the domain. 2x squared is fine, but the natural log x has a domain of only positive numbers. So I cannot substitute in negative radical 2, so that means that my critical value is only positive square root of 2. And if I attempt to find where this rational expression is undefined, that's where the denominator equals 0, so at x equals 0. But this is also not in the domain. I can't plug 0 into natural log, only positive numbers. So my critical value is just positive square root of 2. And now we'll substitute in our endpoints and our critical value into f of x. So here we'll have f of 1, f of the square root of 2, and f of 4. So we have endpoint, critical value, endpoint. So if I substitute in 1, I get 2 times 1 squared minus 8 natural log 1. Natural log of 1 is just 0, so we end up with just positive 2. Substituting in square root of 2, I get 2 times the square root of 2 squared minus 8 natural log the square root of 2. So with the calculator, I will approximate this value, which is 1.227. And then f of 4 is 2 times 4 squared minus 8 natural log 4. And this is approximately 20.909. And now, to summarize, we wanted the x values of the absolute max and min. So we see the absolute max occurs at the x value 4, because that was 20.909. The absolute min was at the square root of 2, which was 1.227 compared to 2. And now we'll go ahead and look at the graph. So here we have the graph of f of x. We see that the endpoint 4 yields the absolute maximum, and it's subtle, but the critical value here at the square root of 2, where the derivative equals 0, is the absolute minimum. Find the max and min of f of x equals sine x times cosine x on the interval from 0 to pi. Ignoring the graph, we'll go ahead and find the derivative. F prime of x is equal to sine x times negative sine x, we apply the product rule, plus cosine x times cosine x. So we end up with negative sine squared x plus cosine squared x equals 0. So in order to solve this trig equation, there are a few different methods. I'm going to go ahead and add the sine squared x to the other side. So I have, when does cosine squared x equal sine squared x? And remember, this has to occur on 0 to pi. So that means on the top of the unit circle. So here, if we're comfortable with the unit circle and familiar, it's like asking what angle can we plug into cosine and plug into sine, and they give us the same value. And they can even give us the same value but with different signs because they're both squared. So that angle, or those two angles that work, are x equals pi over 4 and 3 pi over 4. So these are my critical values. Now, there was another way to solve this. We could also have used the Pythagorean identity and rewritten the trig function up here to make it all the same trig function, and we still would have obtained the same answers. This is just a quicker way, and it really makes sure we know the unit circle. So now we take these critical values and the endpoints and we plug them into the original function. So we are going to go ahead and evaluate f of 0, f of pi over 4, f of 3 pi over 4, and f of pi. And again, into the original function. So we have sine 0, cosine 0. Well, that just yields 0. If we substitute in pi over 4, we get sine of pi over 4, cosine of pi over 4. Each of those are square root of 2 over 2 and square root of 2 over 2, which is 2 over 4, or 1/2. F of 3 pi over 4 is sine of 3 pi over 4, cosine of 3 pi over 4. Now, one's positive and one's negative, so we have sine of 3 pi over 4 is positive rad 2 over 2, and cosine, the x value, would be negative rad 2 over 2, so we have negative 1/2. And then f of pi, so we have sine pi times cosine pi, and sine of pi is 0, so that means that whole quantity is 0. So we went ahead and tested our endpoint, our critical value, endpoint. We're looking for the max and min, so we see the absolute max is 1/2, the absolute min is negative 1/2. So now we can go ahead and take a look at the corresponding graph. Here we have f of x, sine x times cosine x. We can see that at pi over 4 and 3 pi over 4, we do have critical values, places where the derivative is equal to 0, and that is where our absolute max and absolute minimum occurred, not at the endpoints.